Good morning, everyone. Thanks for joining us today for this important webinar. We'll just wait a couple of minutes for more people to join in, and then we'll get started on the agenda today, some explanations about the BMS Alliance and each project, the speakers, and then we'll get down in the heart of the BMS. We'll just wait for a minute or so. Right now you can already see two other speakers that are with me. So my name is Mathias Joussoum. I'll be the moderator for today. And we already have the speaker for the NEMO project, Hosen, and also Hansjörg Kapeller. But I'll go back to it once we have everyone. Okay, I can see more and more people joining. Hello, everyone. And I guess we can start. People will just join in during the meeting. So good morning, everyone. Thanks for joining us today. This will be the first webinar for the BMS Alliance, Advancing New Generation Battery Management Systems. Like I said earlier, my name is Mathias Joussoum, and I'll be your host and moderator for this morning. It's a pleasure to welcome you all. Today's session is the first of the series of webinar organized by the BMS Alliance, a strategic cluster formed under the Horizon Europe program. The BMS Alliance program, it brings together 4 ambitious projects. We have Energetic, BATMAX, NEXTBMS, and NEMO, each working on cutting-edge solutions for battery management systems, the BMS, of course. I'm sure you know this much. So the Alliance aims to advance next generation battery technologies and achieve collective impact. So I'll just start by presenting a bit the BMS Alliance, and then the agenda, each speaker, quickly about a couple of words about each project, and then I'll let each speaker present their own projects. They are experts. So why did we form this cluster, this BMS Alliance? First of all 4 projects were financed under the same call, the same cluster 5 call. We knew we had some things in common from that regard. So once we got in contact and started collaborating together, we saw that we all shared the same vision of collaboration and knowledge exchange. So it made a lot of sense to organize events together. What is interesting with the BMS Alliance cluster is that each project brings its unique strength, and through collaboration, we are amplifying the project's impact. Whether it's through knowledge sharing, like I said, joint dissemination efforts, or coordinating events like this webinar, the BMS Alliance is ensuring that the advancements in battery technology reach a wider audience and have a more profound impact. So simply speaking, together we are stronger. Once the projects have more results, we will make sure to share them with events like today. Again, our goal is also to help shape the next policies, industry standards, and we hope to do so for the duration of each project. Now for the agenda of today, you'll be with me until 11:10 once I'm done with the introduction and presentation explaining the goals of today, and then we will go to BATMAX and the coordinator of BATMAX, Mikko Pihlatie. He will present the goals and more in detail what this project is about. We will then follow with Hansjörg Kapeller, coordinator of the NEXTBMS Project. He's already on. Following that, we'll go to the NEMO project with Dr. Sazzad Hosen, coordinator of the NEMO project. He is also connected. You can see him right now. And we will finish with Ahmed Samet, Dr. Ahmed Samet, who is the coordinator for the energetic project. I'll just quickly go into more details about each project, just to fill you in with the very basics of each project, and I'll let the experts complete that afterwards. So first with the BATMAX project, BATMAX aims to enhance battery system performance across several dimensions: safety, reliability, service life, and life costs. One of the project's primary goals is to improve the parameterization of physics-based models for batteries. The approach that BATMAX takes is twofold. First, it focuses on hardware and sensors at both the cell and system levels, collecting valuable battery data that can be used to monitor performance and predict aging. It's not very easy words for someone that is not very technical. You might have seen that. But I'll let Mikko present that just in a bit. He will be the first presentation. As for the NEXTBMS project, Hansjörg Kapeller will be presenting. He's a research engineer at AIT, coordinator of multiple national and international projects. So for the NEXTBMS project, it also focuses on advancing BMS technology, but takes a deep dive into psychochemical processes of lithium-ion batteries. By building on fundamental knowledge of these processes, NEXTBMS aims to develop more accurate and effective models that can predict battery behaviors in real-world conditions. A key innovation in NEXTBMS is the use of optimized sensors and measurement technologies. These sensors will provide critical data that can be integrated in the BMS to improve the predictions of battery states, such as charge level, health, and safety. I hope I didn't say anything wrong. I can see you shake, so that's good. I'll keep on my roll then. For the NEMO project, we'll have Dr. Sazzad Hosen, coordinator of the NEMO project. He's a senior researcher for MOBI Research Group at the Department of Electrical Engineering and Energy Technology. And for a NEMO project, it is pushing the boundaries of BMS by combining both hardware and software innovations. NEMO aims to develop next generation BMS that rely on high frequency sensor data and electrochemical impedance spectroscopy, so EIS, and basically it uses sensors. I'll let you go in more details. What particularly noteworthy about NEMO is how it integrates data-driven approaches with physics-based models. This combination allows the BMS to make highly accurate predictions about battery health and performance, leading to extended battery life and improved safety for both automotive and stationary applications. I'm sure this will be very thrilling and interesting. I can see that we already have now 50 people, so that's very good. I hope everyone will join in, but first of all, thanks for those who joined in while I was presenting. We'll soon get right down to the very, very core of this subject with the speakers. I just have one final presentation to do. Dr. Ahmed Samet, who is the coordinator for the energetic project and also an associated professor at INSA Strasbourg and iCube laboratory. He will be presenting the energetic project, a project at the forefront battery management systems. One of the key objectives of energetic is to support the European Green Deal by enabling cost-effective energy storage solutions. As you know, this is a pivotal factor in greener batteries and greener tomorrow. But I'll let Ahmed Samet, one of the coordinators of the project, present it with more details. Thank you all for your attention so far. And now let's turn to our first speaker of the day for the project. BATMAX, Mikko, are you here? Mikko is not connected yet, I believe. Well, if that is all right with you, we can maybe change a bit the organization, and we'll start with next BMS, if that's all right. Well, I'll give you the hand, Hansjörg.
Now
you
can hear me.
Yes. Great. Everything
is it working?
Yes.
Okay.
Thank you very much.
Yes. Welcome to the first project presentation. Now it's the NEXTBMS project, and I thank you very much also for the kind introduction. And now I will talk a little bit more in detail, technical detail, and what is the special objectives of the NEXTBMS. As we heard already, that NEXTBMS will develop an advanced battery management system which is built on fundamental knowledge and experience, taking into account the physical chemical processes in lithium-ion batteries. And the benefit of the NEXTBMS project is that we would that currently the battery models are based on semi-empirical models, and they are not so accurate. And in the NEXTBMS, we are trying to combine physical-based models together with conventional semi-empirical models, and so that we have the benefit of fast battery models, but also computationally intensive models. And this will be explained in the next slides. Yes, as said, we will combine here. I talked just about that. We will combine here a physical-based battery model. This will run on a cloud, and therefore it can be very computational, high sophisticated level. And on the other hand, we have also an NEXTBMS on the battery or module side, and here we will also implement a semi-empirical based on electric equivalent circuit-based model. And due to the fact that we have a data transferability, we can then exchange updated parameters calculated in the cloud to the BMS wireless. And yes, and this will then be also supported by new sensing techniques, which will we have fiber optical sensors integrated into the module, and this data will be also used for the model on the cloud. This can take into account temperature sensors and strain sensor measured data, and then in addition, we have then in the cloud also running high sophisticated model and control algorithms, which are able to make a prediction based on the sensor data, but also on virtual sensing, so that we can then also have a state of health and a state of, let's say, a kind of state of X of the battery state and behavior, and so that we can at the end implement an enhanced battery management software performance, which allows to increase at the end also safety and also the lifetime of a battery. Yes, to set up these objectives I mentioned right now, we have established 3 technical layers, let's say, which are also reflecting in the technical objectives. We have here at first the advanced physics-based models, adaptable models. Then we have as further very important a base of technical objective is the advanced data acquisition I mentioned already, and then as technical objective 3 we have then also control techniques, and we have here also advanced state estimators, which can then use either the data collected from during measurements, but also simulation data from the physical based models to make also AI-based a prediction of the and the forecast of the battery behavior and also the health state and conditions. Yeah, this is a more technical picture. Also, we have done. It's taken from our proposal. We have done to overcome our goals and to achieve all goals. We have then identified several pathways. They are running in parallel. As said, we have here. We see here again the technical objectives. Again, we have the modeling, the data acquisition, and then the testing. And then, of course, we are also we are building also 2 prototypes in our labs, consisting each of 12 cells. Yes, and this is let's say an overview of the plan of NEXTBMS. You see all paths are strongly interconnected, and yes, and to structure this work more in detail, we have of course. I will present in a brief way the work packages we have defined to bring us to achieve these goals. So we have here as a starting point, we have in work package 1 we have the we needed to find out what are relevant mobile and stationary energy storage use cases, and we have also the need to define clear and transparent requirements for such enhanced battery management systems. Here we see a graphics about telling us about how the global lithium-ion battery demand is increasing over the last years, and in the next BMS we will investigate 2 use cases, a mobile use case, but also a stationary use case. And here we on the top on the right side we see here a classical battery management system. We will split up this battery management system in a cloud-based battery management system where we can run high sophisticated battery model, and then we have where a data transferability is given with a local BMS, which we have then in the car or in the stationary application. And of course, the battery management system has the opportunity to make measurements by each cell. We can monitor we can perform EIS measurements, current monitoring, temperature monitoring. We have also by each cell implemented protection systems, and of course this will also run combined with a semi-empirical and fast-running battery model on the battery management hardware side. Yes, in work package 2, which all work packages are active, and we have now spent the half time of the project, and therefore I can also tell you that we have already in work package 2 just in connection with the physical based model developing. We have also started with performing aging tests. This is crucial because we need to parameterize our object of investigation, which are NMC cells. In the work package 1, in this requirements work package, we have also defined a proper cell, and we purchased a couple of cells, and now we are investigating that cells, and with that cells we will also build up our prototype. Currently, we are performing an aging test campaign, which lasts about 56 weeks. And here we will induce on a different levels aging effects on the cells. In parallel, you can see we are just performing and setting up the physical-based models. And finally, when we have then gathered the parameters, we can parameterize the model. In the work package 3, we have the second technical layer I mentioned. We have here the sensing and also the battery management software, the hardware, which will be integrated in a prototype. We are building 2 prototypes. You can see here a design sketch with 12 cells, and the prototype will be, the 12 cells are integrated in a housing with integrated cooling and thermal management. And here between the cells we will implement fiber optical sensors. With the fiber optical sensors, we can measure on 5 points the temperature at the corners and in the middle, and then we have also together with the fiber optical sensor the possibility to measure the strain in horizontal and vertical way. We are just performing tests if the sensing is working. And yeah, here we see on top we have also EIS and CMB boards which will be attached to the cells, so that we can also perform EIS measurement during the operation. Yes.
Thank you very much, Hansjörg.
Just the last slide. We have also the work package 4, and this the mentioned 2 use cases will be then also tested in the lab. We will perform a stationary use case and also a mobile use case, and this will allow us then also to upscale this and to prove the BMS together with the prototype we have developed in the NEXTBMS. And this is of course all important for us to also, when the project has ended, to exploit the major outcomes of the NEXTBMS. And thank you very much for your attention, and for I think I needed a little bit more time. Thank you very much.
Thank you very much. And now we're going to Mikko this time. I'm very sorry for the technical issue we had a bit earlier. You should now have the option to share your screen, Mikko.
Yes, can you hear me to
Yes.
start with? Perfect.
I can hear you.
And now I'm aiming to share my screen.
Yes, we can see your screen.
But is it the right one? Because I can't see which one is being shared.
Yeah, it's
Do
the
you
right
see
one.
a presentation?
Exactly, I see the presentation.
Okay, great, good to know.
You just need to put it in full screen. And we just don't have your camera on. We can do it without if you
so
want.
far I wasn't able to activate it, but now I think should
now
be
it's
there.
Perfect. Yeah, we see you, Mikko. Okay, yeah, sorry we're running it just a bit
Perfect.
late. We'll have 2 minutes delay for later. Okay, go ahead,
Yeah.
Mikko.
Thank you so much. And sorry for the technical confusion. Here I'm online. Perfect. Nice to meet you all. And greetings from Finland, from VTT and Espoo. I'll be happy to share some insights on our BATMAX project, and I will keep it quite short here today. So I will not bore you with the organizational charts of work packages and how they flow. We chose to present more on the content that we are working with. Battery management by multi-domain digital twins is the core of BATMAX. So of course we want to contribute to the next generation of battery management, and the main objective, as very clear from the call, improve performance, safety, reliability, service life, lifetime cost, and then really to bring the battery management as a whole to a next level, and by utilizing the digital approaches that are increasingly there. So for that, we start really from physics-based modeling, and we think that the key there will be to have a more technology agnostic approach for and a framework for efficiently parameterizing physics-based models. So then we can really deal with the aging, the degradation, physical and chemical processes that take place in battery cells, and understand how that links with performance at higher level, at module, pack, and system level. Hardware and sensorization are essential elements of the call and of BATMAX project. So we are bringing that into 2 prototypes. Seems a bit similar to the previous project. So 2 prototypes of 48 volts each, equal design will be produced. And then we can also, through this duplication, to have cover more space, parameter space, and do several tracks for validating also towards the use cases that we want to reach. It's a cross-cutting approach, really. Besides the physics-based modeling approach, hybrid and AI-driven, data-driven models are there. And between the physics world, physics-driven modeling world, and the data and AI, so we want to be able to hybridize various types of approaches depending on the application and the levels, the size of the system that we're twinning, and so on. And finally, the adaptable battery management system. So we have at the corner, at the center, the digital twin, and then we move across the multiple scales from really nanometer scale materials, composition, physics, chemistry of materials, microstructures, all the way to scaling up from materials, cell components, composite structures of cells, integrating those to different form factors of cells, to modules with additional structural elements, sensors, data collection, physical BMS, and then reaching that up to a cloud, which will be hosting the digital twin. So equivalent circuit models, physics-based models, data-driven models, machine learning, and AI-driven support. So that's, again, building bridge between the material science and then the end use and applications, where we, in the end, we have some reference use cases. For example, I just mentioned one here, maritime vessels with the battery electric ships. And as we know, they are growing, so there could be megawatt hours of batteries in this kind of system. So it's really a large scope to cover. So we want to understand what are the requirements and also the approaches to cover this. So as said, there's lab scale prototypes, and for those we have Fox BMS in the physical side of the prototype, and then we have the cloud hosting the digital twin high fidelity models. We can do that for the prototype size, but then for the kind of the validation track here is with real application systems. And I mentioned the marine vessels, but also we have stationary storage, heavy duty on-road vehicles, off-road machinery, and so on. So the multiple use cases we can work with. So the two-way communication needs to take place between the physical battery system and the BMS, and then the digital twin. And then we have the database, and the modeling world takes place here on the right side. And then we have the model construction and structure in the physical BMS. Let's go forward, not to spend too much time. So the physics-based modeling, we are starting with extensive use with the BATMO physics-based modeling pack developed by Sintef, one of our partners. And then, of course, there are some other options out there. And one of the tasks here is really also to build a bridge between the physics-based detailed models up to system level with the various approaches for model order reduction. On the sensorization and BMS, So this is one of the proposal stage charts here. So we have the cells and the 48 volt module. Cell level EIS is one of the approaches here. We have additional sensors printed on the cells, for example, for temperature, pressure, deformation, and so on. And then there will be the data collection, dealing with the data with the slaves and the masters, data collection through the EIS unit. And all of that will then link with the cloud side and the data platform. So it's really a two-way street to then for the cloud side to be able to play back into the physical side of it. Data analytics and AI. So I already covered the physics-based models, data-driven approach. We have raw data, we have laboratory data, literature data, and also the real-life reference system data. So all of this needs to be processed. We have a data platform ready at VTT. We will host it, and also host the digital twin and the framework that it will be building on top of the data platform, and collecting more or less, fusing the different data streams and sources, and also putting together the data and have hybrid modeling tracks. Another approach that we are going for hardware in the loop. This has to do much with the physical BMS and developing that. So we will loop in the digital models with the physical BMS and train different kinds of and test validate the safety sequences of the physical BMS and how it all plays together. So we can model faults, random faults, variations, abnormal conditions, also digital. We don't have to burn cells for that or packs for that, so we can really test the functionalities of the BMS, how to deal with various types of scenarios as part of the comprehensive approach. I think that's it, and here you can see the lineup. We are really proud of the group we have here, VTT coordinating, but there are major contributions from all. Sintef, Fraunhofer, CSCM Switzerland, Corvus from Norway, Valmet Automotive, actually Ion Core, I should stay at this point. They have changed their brand name, ABEE, Lumency for sensors, EDF for the stationary storage, RTD Talos for communications, and so on. I think hopefully everyone was already mentioned, and besides EU, it's also Swiss national funding here. Thank you very much, and please visit our website and stay tuned for more news from BATMAX.
Thank you very much, Mikko. It was very clear and very interesting. And now for the next presentation, I think I gave you the hand, Dr. Sazzad Hosen. I think you should be able to present. Yeah, we see your presentation.
I think you can hear me and see the slides already.
Yes.
Okay. Thank you again, and I welcome to all the participants. I'm going to present the project NEMO, which is one of the projects accepted in under this call. What is NEMO in brief? Is that it is from the same call, this D209 from the 2022. The budget is close to 5 million, 8 partners. You can see the logos of the partners from Austria, Germany, Belgium, Italy, and Switzerland. And the project is also started more or less at the same time, already halfway through 36 months of project. And the basic information you can also find from the webpage and in our social websites. So what NEMO addresses is quite similar to other projects, but obviously they are complementary to each other. So NEMO will work on the improved signal acquisition and the computational resources. So mostly how to put the models that we develop under this project can be implemented into the embedded system. The validation of the improved state estimators and advanced aging models are also part of the development process in this project. We'll demonstrate the battery lifetime by cell switching with balancing, and also in a module level, very similar to other projects where 2 modules will be developed of 2 types. I will present some of the key parameters of them later on. And also the safety is one of the aspects which are addressed in this project with early failure detection and swelling modeling work. So what is the NEMO methodology? It's just in a quick overview of the slides. The base of the plan is the EIS, electrochemical impedance spectroscopy, techniques from which we will develop our models, and the acquisition of the sensors on top of the regular voltage, current, and temperature is part of the key criterion. Then two types of models are addressed here, mostly physical models and data-driven models. Hybrid models is also one of the objectives. So it's more local processing and developing the algorithms and models and then putting them into the cloud in case of high fidelity or high processing power required, or with close communication with the onboard system. On the aging modeling part, many research has already demonstrated that the pros and cons of different modeling techniques. So we started from there and only focusing on the data-driven and electrochemical models, P2P norm and framework models. The semi-empirical model is not addressed in NEMO, so the data-driven modeling techniques are addressed with an automatic pipeline of the data feeding to the models and then having training and finding the best or the most suitable data-driven technique. On the P2D or electrochemical side, finite element method is used to develop EIS-based reduced order model, and then in the end they will be combined together to produce the hybrid model, having the common benefits of the two types. What is going right now in as part of NEMO, small on cell level and module level activities at the same time. So in the PUB's location, commercial battery cells are getting tested. You can see a sample picture on the photo. Both the first and second life scenarios are considered. 66 cells are now under study with the different cycle life and calendar life conditions, and reference checkup tests are done, and the data is fed to the advanced modeling works and also to the automatic uploading into the cloud, so that they remain in the public domain and can be used online. Some of the results, it's very early at the moment, but I'll show you some of the calendar lab results of the EIS part that you can see after 1 month of storage at high temperature, at high SOC. The battery is already having higher impedance, and the tests are ongoing, and in the coming weeks and months, we'll have more and more cell level aging data available to present. At the same time, in another location of our partner in Grass, battery safety is getting checked. So in a hydraulic press test bed called Presto in the location, and the cell is pressed with a certain load until the internal short circuit point is reached. The test parameters are mostly at 75% SOC. The velocity is 1 millimeter per second, and it's done on 3 cells. And the average result that we have found out that the internal short circuit point was received as 30 close to 37 kilonewton pressure. This is ongoing activity on the cell level, on the safety part, but side by side there will be more activities on the aged cell, similarly with the similar parameters on the cell. Then on the module level, it is already has been already prototypes made at the module level, where 12 cells, similar to the other projects as well. 48-volt battery modules are prepared and systems and tested in systems location. We call it ZBMS, where the batteries, the cell level battery, the cell level Infineon chips are used for the EIS measurement, and the modules are tested for longer term to demonstrate the aging and the performing models and estimators on board system. You can see the schematic of the module here as fully wired system, but there will be wireless prototype version as well later in the project, which we call it ZBMS Plus. The results, I will see some of the other setup pictures in the partner location where the full module is placed under a secure system called Lilabut, and the external devices are used for the cycling and also for EIS. The results show already in the module level. So what we are performing is a module level WLTC cycling to demonstrate that on a real scale at a TRL4 level that the module is capable of performing the estimation algorithms very precisely. So what's coming for NEMO is that the cell level characterization test will be ongoing. So there will be quite a few models developed on cell level and then will be extended to module level before implementing into the embedded system. The ZBMS cycling will also continue in parallel to demonstrate that the modeling works is validated on a module level. Then ZBMS Plus will also demonstrate the cell switching capability and the improvement of the lifetime via cell switching and also with wireless data acquisition. Okay, then I hope I have the right on time. This is the coordination team for NEMO, and thank you for your attention.
Thank you very much. I will now give the hand to our last presenter, Ahmed. You should now have the right to activate your presentation.
Could you hear me?
Yes, I can hear you. On the other hand, what we are seeing right now is attention scores.
Hold on. It's coming. Here we go.
Yes, now we have your presentation. Perfect.
Okay. Thank you very much for having me and for the other sister project of the energetic project. Welcome everyone. So my name is Ahmed Samet. I'm coordinating the energetic project along with my colleague Tejani Misbahi, who couldn't be here today. And the project is managed by Marie Sukanova. We are two researchers from INSA Strasbourg and iCube Laboratory from different research teams, both coordinating the energetic project. I have artificial intelligence and machine learning background. So that's why my presentation will be very computer science wise rather than batteries. But of course, my colleague Jenny has a more energy storage and battery background. So let me talk to you a bit about the energetic project. So the energetic project is stands for next generation of battery management system based on data-rich digital twin. It goes for 13 months since June 2023. The total budget of the project is 5 million. The other 4,100,000 for the European partners and associated partners from the UK has their own budget. In Strasbourg, myself and my colleague Jenny are coordinating this energetic project, and you can see here different ways to interact with us, with the website, with the social media, and our newsletters. Okay. As I said, the project has a consortium of 13 different partners, so it's quite a wide consortium from 6 different countries, mainly France, Belgium, Germany, UK, Serbia, Estonia, and Luxembourg. So of course, it's a consortium of industrial partners and a researcher from academia. Mainly as industrial partner, we have EDF, Capgemini, and Typhoon Hill. And of course, the academic partner, mainly from France, in Strasbourg and FEM2ST, from Luxembourg, SNT, HKA from Germany, and of course, Coventry University and Bath University. So the consortium, as I said, is wide, but we have a different expertise, mainly related to BMS, AI for time series data, or AI for images. We have, of course, quite industrial different partners specialized in digital twins, since we include digital twin in our proposal. We have, of course, different partners related to the data collection, the testing, the hardware abstraction. So all these different partners are working together in a synergy in order to make the project progress. So what's the aim of the energetic project? Yeah, to summarize it, it aimed to develop the next generation of the BMS. As the other presentation have said, the sister project, we all aim to imagine this next generation of the battery management system, how it's going to be, how it's going to work under the first and the second life, in aim to reduce the total cost of ownership. Of course, when we say first life, it's mainly mobility application, while second life is mainly for stationary applications. And the energetic project aimed to contribute in the field of enhanced sensing technology. We combine both data-driven machine learning model with multiphysical experts, and to ensure, of course, the safety of the battery. And we not only aim to predict and monitor the remaining useful life of the battery, but we also, of course, thanks to the digital twin, we aim to understand what are the different reasons that made the battery health degrade, and to explain that to the user. So that's where, of course, our team brings some new information, new insight, and mainly related to artificial intelligence domain. So if I have to summarize the whole framework, so basically we rely on, from the data part, on two types of information, mainly the time series data, so all the data related to the battery health and the battery information, such as the current, voltage, the temperature. And we also will rely on thermal images in order to investigate how the thermal part of the battery is evolving through for the different use of the battery. Of course, we are going to have two different models. So the physics model, so multi-physics model, which is going to be developed by our partner from FEM2ST and Université Belfort in Montbéliard. And we have the data-driven model. Both of them are going to combine under this we call smart BMS, a smart digital twin BMS, in which, of course, we include the different features. So it not only aimed to predict the SOX prediction, so mainly the state of charge, the state of health, but also remaining useful life. We aim as well to understand what are the different failures that can happen to the battery. And of course, what makes it different is we try to provide an explanation why we come up to that prediction. And we do that on a real-time testing, of course. Of course, since we are using BMS, it's somehow limited in terms of computation. So that's why our BMS is interacting with the cloud, of course, to do the most extensive computation and data storage. And this digital twin will be applied on, as I said, as in the first life for the mobility application, and the second life for stationary application. So let me make a focus here on this special feature that I think make energetic project specific in this part. So we aim to investigate the explainable AI domain in artificial intelligence. So of course, we all know that deep learning model are designated as black box model because they provide quite accurate predictions, while of course we still not confident about and not transparent about that prediction. So that's why we try to investigate how to make those models more explainable in order to help the user to understand how this model came up to that prediction. So we integrate to that model time series data and thermal images. And the machine learning black box model will make a prediction, and we will try to make it explainable and provide explanation about why we come up to that degradation. So we developed quite different models. Here I'm just detailing one of them. So basically it's called a sequence-to-sequence model. So we take a whole cycle window of the battery degradation, and we try to predict the full curve of the SOH while we try to be more explainable. So of course, we provide, of course, a model based on transformers model. And the model, of course, provide the full curve of the SOH based on the last 25 cycles. And it provides us with a few insights about what are the cycles, what are the cycles related to the degradation. So mainly here you can see it is the cycle 15 and cycle 23. So of course, at the end of project, we aim to combine the data coming from thermal images, time series data, and multiphysics model. Those three types of data we will try. They provide explanation, but they provide explainable prediction. And those explanation we will try to understand them and provide at the end a final prediction with the different explanation coming from the images, the time series data, and the multiphysics model. So as well, our project is it's an open source, an open, I would say, project in which, of course, the data aim to be shared with the different members of the consortium. So we are also storing our data coming from our test bench in a special platform that we made it available to the different member of the consortium, providing metadata in which we store the style data sheet, the testing protocols, as well the information about the publication. And we aim, of course, by since the project is progressing, that from the test bench we store the data directly from the in the platform, that it could be shared and by the different member of the consortium. And of course, at the end of the project, few of our data will be shared. And I will finish my presentation with this last slide by saying the final outcome of the project will be new physics and data approach for battery management with the potential to enhance performance, lifetime reliability for transport and stationary application. And we combine physics and data-driven approach for battery management, facilitating predictive maintenance, knowledge-driven end-of-life management of battery system, and the development of more accurate degradation models. We stick to TRL 4 by the end of the project. Thank you very much for your attention.
Thank you very much for your presentation. I think you can keep your camera up, but I'll take the presentation again. I think all the speakers can put their cameras on. That way, for the Q&A, it might be easier. Great. Now you should see the Q&A session, because that's now. And for the questions, we already have two, and they're regarding the presentations. Two different people asked if the presentations would be available somewhere. Are you willing to share your presentations? I'm asking each speaker. You can answer in turn.
For BATMAX, yes.
For energetic, yes.
Yes, also for NEXTBMS.
Yeah, I'm
Okay.
for NEMO too.
Well, that's great. I see the names. I'll try to send them by email directly to you. I believe I have that option. If I don't send them because it doesn't work, you can just contact me on the energetic webmail or on the social media, and I'll get in contact with you with each presentation, if that works for you. And if you have more questions, don't hesitate to write them in the channel. For now, For now, I don't see any questions. Is this webinar recorded and will it be available? Yes, it is being recorded. It will be discussed, but it should be shared on YouTube if you want to go back on some specific parts. I can see someone else wants the PPTs, so that's good. I guess you were captivating. Here I see another question. This is Monica Giannini. I'm the project officer of the 4 projects from Cinea, and I would like to congratulate for this first webinar and encourage additional webinars in the future. Well, thank you very much. That's great to hear. It's always very nice to have good feedback. Will your presentation be sent to those asked? Yes, I'll send them to you. There is a question from Pranti Twahid, and he asks, your data is shareable or not energetic?
It should be by the end of the project. Few of our data, if not, I think a few of our data is going to be sensible, especially the one coming from our industrial partner. But some of our data that has been tested in our lab should be available, and we intend to share one of our data very nearly in the coming weeks in a journal paper.
The next question is, hi everyone, my name is Federico. I write from Fraunhofer IFAM Bremen. I have a question for Dr. Pihlatie. Can you Plaise, P-L-A-S-E, I don't know, Plaise, explain, oh please, I believe, please explain a bit better the printed sensors concept. So Mikko, I believe that is for you.
Yes. So we have, I think I mentioned Lumency from Belgium working on that. So it's thin printed sensors that we are currently working on an approach. It's printed on substrate, preferably in the whole cross section of a pouch cell, so we can print it to get temperature distribution, pressure distribution, so localize the parameters we want to address. I think those two are the most interesting. Then we're working if we can get some noise measurement and so like additional sensors. So each of the printed sensors are then put on the substrate, which is adhesive that can be mounted on the cell. In this case, a pouch. It could be some other form factor as well. So it's potentially each cell carries the sensors that then each have their driver, and then we collect the data from those with the BMS and bring it to the BMS interface.
So next question is regarding the YouTube link. Will it be shared? It depends if the YouTube is available as fast. Otherwise, it will be shared on each social medias from all the 4 projects, so it will be accessible, I believe. Next question is, could the group share any insight to cell level EIS versus model level EIS? Does anyone want to start?
Maybe I can take it quickly. So from NEMO side, we are mostly working on the cell level EIS chips. So module level is not part of NEMO, but is certainly a direction that is going forward. The partner that we have with us, Infineon, that produces the cell level chips, are also working on module level, I believe. But in future, I think there might be a good solution if EIS becomes one of the promising techniques to develop models.
Yes, Mikko? I can see.
Just a brief comment. Yeah, the ambition we want to push here, because it's TRL 4 or 5. So really, it's the cell level, detailed cell level understanding we want to push. We think that's where the differences between cells and the performance in detail gets. And we think we can at this point cover that quite well at the 48 volt level. Whether or not we can really scale up to large systems up to megawatt hour size at cell level, at this level of detail, that's one of the research questions we have. But yeah, for the prototypes, absolutely at cell level, we think the diagnosis needs to be there.
I can see that the time is really running out. We have two last questions that might be very interesting for everyone. If that's okay for everyone, we can run a bit overboard. If not, you can just leave the call. Thank you very much for attending. The first question is also, I am curious about the AI feature in energetic, the ML and AI model for understanding the mechanism are integrated in the same algorithm or two stages.
Yeah, I can answer that question. So definitely in the lab we are investigating different XAI models, explainable models. So we have different way to do it. If you look to the literature, you can see that there are different approaches that have been developed in the literature, mainly with LIME and CHAP. These are the main two tools for explainability, but they are in AI domain, they not very reliable, and they are less used right now. So what we develop our own model. So basically the model that I have presented is mainly the explanation is already provided in the model itself with the transformers. While there is another approach is based on counterfactuals. So basically is to have the model and to input different scenarios, I would say different variation of temperature, current and voltage, and to check the output of the model and try to explain it with the different variation of the input, and to find what are the different input that make change the prediction. That's the counterfactual part that we are investigating right now with the different PhD students, and hopefully I can present something related to that in next webinars.
So the final question, oh, I see more questions, but I think we'll just have to have that final one. I can send them by email for the other questions. This one is from Emanuele Michelini. What is your perspective on the current state of the BMS industry in the automotive field, and how transferable do you think your research results are to real-world applications? I think that's quite general for questions everyone can answer. Who wants to start? No one. Do I have to decide? Hansjörg, do you want to go?
Yes, of course, this is from NEXTBMS side. We are also, of course, it is very important that we will also pave the way to develop here a battery management system for the future and also for the industry, which is capable to be equipped with a battery model, which is really a reliable model, and on which it is running on the battery management system itself, but also it's coupled via cloud, so that we can improve the functionality of the battery management systems. But in the way we develop that, all things are developed in a modular way, and it can be easily transferred to industry or mass production. And due to the independence and the possibility to implement high sophisticated physical-based models into the cloud, it is possible to enrich the battery management system with a high functionality, which allows to forecast the operating and the lifetime of the cells. And yes, of course, we can also implement a lot of in the battery management system also additional and very innovative sensing concepts are introduced. We have heard the EIS chips. Also in the next BMS, we are using single EIS chips, which are on cell basis, but this cell we are using provided from our partner NXP EIS sensors chip sets, which are also able to measure current and voltage and also the EIS and temperature, and this can be done by a range of 8 milliseconds millihertz up to 8 kilohertz, and together with this strain measurements and the couple of data which can be fed then to the large models in the cloud. It is it's very promising that the battery management systems of the near future are providing really improving and paving the way forward that to increase the battery implementations in electric vehicles, but also for stationary applications, of course.
Does anyone want to add a last word, or are we're good? Okay. Well, I wanted to thank you all, and specifically our speakers, for the insightful presentations today. Thank you all for joining us. Today we explored the incredible advancements being made by the energetic BATMAX, NEXTBMS, and NEMO projects. I put forward right now our social media. Don't hesitate to follow us. We'll keep you updated with all the progress from each project. I didn't mention that we received multiple messages thanking the speakers, and it's good to see that you enjoyed this webinar. Please, again, follow our social media. We'll keep you updated on the progress of each project and on the next webinar from Energetic. Thank you all for joining today, and have a good lunch probably. Bye, everyone.
Thank you.
Thank you. Bye-bye.
Thank you very much. Goodbye. Thank you.
Thank you. Bye.